In today's video, we're going to look at the key points in Chapter 4, Work, Energy, and Power. First, what is work? In everyday language, work might be writing an essay or doing homework. However, we say the process of energy transfer is called doing work. Work is a new quantity in physics. Work done equals the amount of energy transferred. Let me give you one example. If I push a box and the box moves, and we can say I've done work to the box. Since work done equals the amount of energy transferred, that means I have transferred my energy to the box. But how could I know what is the amount of energy being transferred? We can calculate the work done. In physics, we define work equals force times displacement. Okay, here. Work equals force times displacement. If the force is parallel to the displacement, this is the only case we will discuss in this chapter. So this is a new quantity. And then the SI unit of work, it should be SI unit, okay? The SI unit of work is joule. SI unit means this is an international system unit, okay? So it's like a standard unit of work. And then suppose if 4 Newton force moves an object 3 meters, then the work done we can calculate, okay? We use W to represent work. W equals force times displacement. In this case, force is 4 Newton, so 4 times displacement is 3 meters times 3. 4 times 3 is 12. Remember, the unit is joule, so the work done is 12 joule. And then work is a scalar quantity. Do you still remember what does scalar mean? A scalar quantity means this quantity only cares about the magnitude. Okay, there's no direction in this number, okay, 12. However, we use positive and negative sign to represent the direction of work. Okay, sign of the work. When the force acting on an object is in the same direction as its displacement, energy is transferred to the object. And we say, in this case, the work done by the force is positive. Let me give one example. Suppose now I push a box. Okay, now I push a box to the right. Okay, since I push the box and this box moves, that means I have done work to the box, right? And we know that work done equals the amount of energy transferred. So that means I have transferred my energy to the box. Okay, so in this case, we say the work done by my force is positive, and the energy is transferred to the object, which is the box. Okay, so this is positive work. Okay, so in this case, okay, my work will be positive. How about the negative work? When the force acting on an object is in a different direction as its displacement, energy is taken out of the object. The work done by this force is negative. Okay, so it's peculiar, right? It says an object is in this different direction as its displacement. How could it be possible? Let's go back to our example, okay? This box, look, suppose I push this box and this box move, okay? However, I only push the box at the first second, okay? Then the box should keep moving, right? But at some instant, this box will stop moving. Let me ask you, why this box will stop moving? Because there is a friction against the box, right? There is a friction to the left-hand side. Okay, to the left against this box. Okay, let me ask you, now this force is also acting on the object. Okay, I mean this friction. And we examine this force, okay? The direction of friction and the direction of its displacement, they are opposite, right? The direction of friction is to the left and the movement is to the right. Okay, in this case, we say the work done by force is negative. Okay, so we can say the work done by friction is negative. If the work done by friction is negative, what does that mean? That means energy is taken out of the object. Okay, why? The reason is the energy of this box is given back to the ground. You may think, how? Okay, if you touch the ground, you may feel the ground is getting hot. Why? Because now the ground is receiving thermal energy. Okay, that's why this box will stop moving and the ground is getting hot. Now let's look at exercise 1. A trolley of mass 200 grams is pushed by a horizontal force of 0.4 newtons. It travels a distance of 3 meters and experiences a friction of 0.1 newtons. Part A. Find the work done by the applied force. Okay, so I write as W1. The work done by the applied force equals force times displacement. Okay, so the applied force is 0.4 newton. 0.4 times the displacement is 3. So 0.4 times 3 is 1.2. Remember, the SI unit of work is joule. So 1.2 joule. Part B. Find the work done against friction. Okay, I write as W2. Okay, so still the same. In this case, the force is friction. Okay, the friction is 0.1 newton. So 0.1 times displacement. Okay, still 3 meters. Okay, times 3. So that would be 0.3 joules. Part C. Find the energy gained by the trolley. Okay. Let's think. Okay, in part A, the work done by the applied force is 1.2 joule, right? And we know the direction of the applied force and the direction of displacement, they are the same. That means the answer should be positive. Okay, that means I transfer 1.2 joule energy to the trolley. But in part B, the work done against friction, the direction of friction and that of displacement, they are in opposite. That means the answer is negative. What does that mean? That means the energy of the trolley is taken out. Okay, and the energy is giving it to the ground. Therefore, the energy gained by the trolley will be W1 plus W2. That would be positive 1.2 plus bracket negative 0.3. So that would be 0.9 9 joule. So that means the energy gained by the trolley is 0.9 joule. Now let's talk about different forms of energy. We have two big groups of energy: mechanical energy and non-mechanical energy. Let me talk about the latter first. We have 5 examples about non-mechanical energy. The first one, chemical energy. Chemical energy is energy stored in the bonds of mechanical compounds, like atoms and molecules. Examples include batteries, food, gasoline. When we eat food, the chemical energy in the food is being transferred to our body. That's why you have energy to watch my video now. Thermal energy. Thermal energy is produced by the movement of molecules in an object. In hot things, like a hot drink, hot tea, the molecules move very fast. The faster the molecules are moving inside an object, the hotter the object will be. Nuclear energy. Nuclear energy is the energy released during nuclear fission, especially when used to generate electricity. Electrical energy. Electrical energy is a form of energy resulting from the flow of electric charge. The last one, acoustic energy. Acoustic energy is actually sound energy. Okay, sound energy. Sound energy is the energy that we can hear. It is a type of kinetic energy that is made from the vibration of matter. Now, let's talk about mechanical energy. Mechanical energy is a collective term of kinetic and potential energy. For potential energy, it can be classified as gravitational potential energy, abbreviated as GPE, and elastic potential energy, abbreviated as EPE, okay, and kinetic energy. It is abbreviated as KE. Now I will talk about these 3 kinds of energy in depth. First, kinetic energy. Kinetic energy is the energy of motion. Any moving object has kinetic energy. That means if something is moving, we can say this object has kinetic energy. The faster an object moves, the higher its kinetic energy is. How do we calculate the kinetic energy of an object? Kinetic energy of an object equals 1/2 times mass times velocity squared. You may think, of course, velocity is related to kinetic energy, right? Because KE is the energy of motion. But why? Mass is still related to the kinetic energy. Let me give you one example. Suppose we have 2 guys, small guy and big guy. Okay, so they are both running at the same speed. Okay, they are both running at the same speed. Let me ask you, do they both consume the same amounts of kinetic energy? Of course not, right? This big guy, it should consume a larger amount of kinetic energy so that they can both run at the same speed. Okay, so that's why kinetic energy of an object equals 1/2 times v times m times v squared. Okay, so mass and velocity, they are both related to kinetic energy. Let me give one example. The kinetic energy of a bullet of mass 5 gram moving at 300 meters per second is equal to a half times m. Okay, so mass is 5 gram. However, we have to convert it to SI unit, which is kilogram. Okay, so 5 gram is equal to 0.005 kilogram times V squared. Okay, V is 300. So 300 squared. And that will be 225 joule. That means the kinetic energy of a bullet is 225 joule. Now, let's talk about gravitational potential energy. Gravitational potential energy, abbreviated as GPE, of an object depends on its vertical position. GPE is actually the work done by gravitational force, which is gravity. The higher the object is, the more GPE it has. I know you don't understand. Let's derive the formula. GPE of an object equals mgh together. Suppose there is a ball falling to the ground. Okay, so there is a ball and it is falling to the ground. Why this ball is falling to the ground? Because we know there is gravity acting on the ball. Can we calculate the work done by gravity? Yes, work done by gravity equals force times displacement. Force times displacement. Okay, F stands for force, S stands for displacement. Now, this F is actually gravity, right? By Newton's second law of motion, we know force equals mass times acceleration, ma times s. Okay, since F is gravity, this small a, it will be small g. G is the acceleration due to gravity. So that means we have mg times s. Okay, this small g is the acceleration due to gravity, and small g is approximately equal to 9.8 meter per second squared. Okay, and this s is displacement, right? If I let this h be the height above the ground, that means the displacement will be h. So that will be mgh. Therefore, the work done by gravity is equal to m times g times h. And we know work done by gravity is gravitational potential energy. Therefore, we can say gravitational potential energy of an object equals mgh. Okay, so remember, the higher the object is, the more gravitational potential energy it has. Now, let's give you one more example for calculating the gravitational potential energy of the object. Okay, suppose there is a rock. Okay, there's a rock there. Now, we want to calculate the gravitational potential energy of the rock. What should we do? First, GPE of the rock is equal to mass times small g times h. Okay, so what is the mass of the rock? The mass of the rock is 75 kilogram. So m is equal to 75. How about small g? Do you still remember what is small g? Small g is equal to approximately equal to 9.8 meter per second square. Okay, but usually we use g is approximately equal to 10. It is easier for our calculation. So we substitute g equals 10. And h is the height, right? Height is 4 meters. So we substitute h is 4 meters. Then we can calculate the answer will be 3000 joule. Therefore, the gravitational potential energy of the rock will be 3000 joules. One more example. Suppose this car is rushing to the peak. Okay, it's rushing to the peak. This car will stop moving when it is on the peak. Stop moving when it is on the peak. Why? The reason is the kinetic energy is transferred to the gravitational potential energy in the process of going up. Okay, so you can see the gravitational potential energy, no, the kinetic energy is being transferred to gravitational potential energy, GPE. Okay, you should have GPE. Okay, when the car goes down, the kinetic energy of the car is being converted into the gravitational potential energy. So you can see when the car is rushing, it's going down, the gravitational potential energy is being converted into kinetic energy. That's why this car, when it goes down, it will move very fast. Okay, the reason is the gravitational potential energy is being transferred to kinetic energy. Now let's talk about elastic potential energy. Elastic potential energy, abbreviated as EPE, is the energy stored in an elastic object when it is stretched or bent. It depends on its material and the extent to which it is deformed. I know you don't understand. So let me give you an example. Let's look at the diagram on the right hand side. When you shoot an arrow, what would you do? You will pull the bow, right? When you pull the bow, your chemical energy is being converted to the elastic potential energy. Okay, so let me write it down. When you pull the bow, your chemical energy is being converted. Your chemical energy is being converted into the elastic potential energy of the bow. Okay, so what? At the moment you release the bow, this elastic potential energy is being transferred to the kinetic energy of the arrow. That's why this arrow will go very fast. Okay, the reason is, first, you transfer your own chemical energy into the elastic potential energy of the bow. At the moment you release the bow, the elastic potential energy is being converted into kinetic energy of the arrow. Okay, so that's why this arrow will go very fast. Okay, elastic potential energy. Let me ask you one thing. Do you know why gravitational potential energy and elastic potential energy, they both have potential in their name? Okay, elastic potential energy and gravitational potential energy, they both have potential in their names. Why? It is because they both have the potential to convert its energy into kinetic energy.